Welcome to MRU E-Learning powered by Mallaradi University. So today we'll be talking about design and analysis of algorithms. And I'm Sanjay Kumar Jaiprakash Hamilpure, Assistant Professor, Department of AIML, School of Engineering, Mallaradi University. So these are the contents for today's e-learning. The first content is notion of algorithm, followed by analysis of algorithms. In that we are going to discuss about order of growth and the three possible efficiencies, followed by asymptotic notations, and at the end we are going to have one analysis of a non-recursive algorithm. So starting with a prerequisite. So before we understand design and analysis of algorithms, first of all we need to have a basic idea of a data structure and a programming language, followed by a mathematics. So this is the basic prerequisite. And starting with a notion of algorithm. So the concept of algorithm is all about, for a given problem, how to solve, or for a single problem we'll be having n number of solutions. But among those n number of solutions, which is the best solution we need to go for. So based on that only this entire subject is all about, that is efficiency of an algorithm. So starting with the basic definition of an algorithm is a step-by-step procedure to solve a given problem in a finite number of steps by accepting at least 0 or more in number of inputs to produce the desired output. So that is all about a basic definition. And as we can see in this particular notion of algorithm, we'll be able to observe here for a given problem how an algorithm is going to accept the input, and based on that input how it is going to convert to a program, and later on it is going to provide it to a computer with respect to a particular language, and there we are going to provide input so in order to produce the desired output. So this is what the exact notion or concept of an algorithm is all about. And moving towards the basic characteristics or properties of an algorithm, there are basically 5 fundamental characteristics or properties of any algorithm, so which includes input, output, finiteness, definiteness, and effectiveness. So where input is all about every algorithm should be able to accept 0 or 1 or more number of inputs. So that is the first property or characteristic of an algorithm. And coming to the second characteristic, that is output, the algorithm should produce the correct result. That is, whatever the required result is, the desired required result is required, that it should be able to produce. So that is all about the second criteria or the second characteristic. Moving towards the third characteristic, that is definiteness. So here definiteness is all about each instruction should be clear and unambiguous. It should not create any problem. So anybody can able to understand what the algorithm or a rough idea we have written. So that is all with respect to a definiteness. Moving toward the fourth characteristic of an algorithm is finiteness. So this finiteness is all about any algorithm should terminate after a finite number of steps. It should not go, or it should not take more number of steps. So then that is not called as an algorithm. So this is one more basic property of an algorithm. And moving towards effectiveness, that is the final characteristic of an algorithm. That is, every instruction should be simple and should transform the given input to the desired output. That means anybody can write an algorithm with the help of simple paper and pencil. So that is all with respect to effectiveness. And not only coming to this particular definiteness, but it should also be feasible. Whatever the solutions we write for any problem, that should be feasible too. So that point also I would like to add under the property called definiteness. So moving towards an algorithm specification. So this algorithm can be described in 3 ways. The first one is natural language. The second category is graphical representation. And third one is pseudocode. So natural language is like this, the English language. So normal human language, how we talk. So in that way also we can write. But in natural language, we cannot express any programming constructs or instructions or statements. So moving towards the second way of writing an algorithm is graphic representation. So this is also known as a flowchart. So flowchart has got its own conditions and criteria. So which symbol has to be used for starting of an algorithm, or for condition check we are going to use diamond, and for end and beginning of any algorithm will be indicated with an oval, so rectangle, parallelogram. So all these symbols we are going to use for representation of an algorithm in terms of a flowchart. And moving towards the most familiar and most used method or a way for expressing an algorithm is a pseudocode method. This is going to be the combination of natural language followed by a programming language. So this is going to be a mixture of both. That is, natural language also we can use, and program constructs also we are going to include inside this pseudocode. And those who will be having a basic knowledge of a programming language, they will be writing a pseudocode rather than a natural language or a graphical representation. So moving towards basic example of a pseudocode conventions, here we'll be able to see the algorithm which finds and returns the maximum of a n in the given numbers. So this is the basic one example for writing an algorithm to find an maximum element from a array A of size n, input n. So initially what we do here, we are just going to start with a term that is an algorithm colon, and the algorithm name would be written, and for user understanding and readability purpose we are going to add a comment lines. So that comment line can be a single line or a multiple line, depends on the requirement. If the algorithm is bit complex, then we need to go for, or we can go for having a multiple comment lines. So after moving towards a third line here, this is going to be the beginning of our algorithm logic, where we can users that this is the beginning of the program or algorithm logic, and this is going to be the basic initialization and declaration come initialization. Then we'll be going for iteration, that is with the counter variable I is equal to 1, that is 2 to n, because the result the first element is stored into a result variable. Then one by one element we are going to compare. So based on the comparison, the result will be updated into a variable by name result, and the same result will be returned here. So this is how we are going to write a pseudocode, and in this pseudocode we'll be able to clearly see that this is a combination of both, that is a English, that is natural language, followed by a pseudocode. So this is how most of the programmers or the students will be able to understand in a simpler way. So coming to the analysis of algorithm, the major purpose of studying this entire subject, that is design and analysis of algorithm, is to design the most efficient algorithms in terms of time and space consumption by any program. So the efficiency of an algorithm depends on basically two factors. The first factor is space efficiency. The second factor is a time efficiency, or we can also call it as a time constant. So here the term efficiency talks about the total amount of space and time consumed by our program. So nowadays, as the space is no more a constant, as we are having cloud computing, a cloud storage. So for that reason, we are not going to consider a space efficiency as a major challenge in our designing or analyzing any of the algorithms. So we will focus more and more on time efficiency, because we are going to analyze, or we are going to conclude so and so algorithm is much efficient in terms of time consumption by that particular algorithm. So only we are going to focus more on time efficiency. So the major components that affect basically the time efficiency are listed here. So the first component is speed of the computer. The second component is choice of the programming language. Third, it could be a compiler used, and the choice of the algorithm, and the number or size of inputs or outputs. So these are the basic components which are going to affect most of the time efficiency of any algorithm. But we cannot consider the first criteria or the first component, that speed of the computer, because nowadays we are having varieties of computer capacities. It may be a 32-bit machine, 64-bit machine, or 128-bit machine, and more. So we cannot simply judge the efficiency of any algorithm with respect to the speed of computer. So for that reason, we are going to discard the first component. And choice of the programming language. As we all know, C programming, C++ programming, Java programming. When we compare all these programming instructions with the Python programming language, So, of course, we all know that Python requires a very limited short writing code, ease of writing code. So, because of due to that reason also, we are not going to include the choice of the programming language, because the one single program, what we write in a C programming language, will differ in its length and size with respect to Python programming language. So hence we are not going to include the second component as well to analyze the time efficiency of the algorithm. So coming towards the third one, the third component also we are going to discuss, because the compiler, what type of compiler we are going to use. For basic programming languages in Java and all, we are going to use compiler. When it comes to Python and all, we are going to use interpreter. So again, we cannot decide or judge or conclude the efficiency of any algorithm with respect to a compiler used. So we focus purely only on the choice of the algorithm. This is the major criteria where we are going to add a component or a major component for deciding the time efficiency of an algorithm, or followed by the number of inputs or the size of the input or output of that particular problem. So these are going to be the two major components we'd like to consider for our time efficiency. So moving towards the analysis of algorithms, how to compute the running time. The next question is going to be how to compute the running time of algorithm using basic operation, or how efficiency is analyzed. So before starting this, I would like to just go through what is basic operation. So in any algorithm or whatever the pseudocode we write, in that, irrespective of any problem, any instruction in an algorithm which is going to consume more amount of time or which is going to execute more number of times, that particular instruction we will be calling it as what? A basic operation. So statement 1 in our algorithm may consume least amount of time. Statement 2 also may consume least amount of time. But statement 3, if it is consuming more amount of time compared to all other instructions in our algorithm, so then in that line we will be having our basic operation. So that line may contain any logical or conditional statements, so only it will be having more number of operators in it, and automatically it is going to consume little bit more amount of time compared to other instructions in our program. So such statement or instruction, we call it as a basic operation. So now coming to this, how time efficiency is analyzed. For any algorithm, the time efficiency can be analyzed or determining the number of times basic operation is executed. That means for any algorithm, how much time is consumed by our basic operation. So based on that, we are going to analyze the time consumed by our algorithm, and the running time will be written as T of n. Here T is nothing but a time and n is representing the size or the number of input for that particular problem. So we are going to call or represent it as a T of n, and T of n, the expression will be written as T of n is approximately is equals to B into C of n. Here I'd like to tell the terminologies where T represents the running time of the total running time of the algorithm, and the lowercase letter n represents the size of the input, and B is the execution time for the basic operation. So the final C term represents the number of times basic operation is executed. That means total number of times the basic operation is executed in our algorithm. So this is together will provide us a total time consumed by our algorithm. So this is how we are going to analyze the time efficiency for any algorithm. So coming towards the next concept, that is order of growth. So here the basic idea we need to understand, that is order of growth. And for what values of n, that is it may be input size or the number of inputs for any algorithm, we find the order of growth. So we expect any algorithm or whatever the algorithms we write or which we feel that efficient, which are faster. So to work faster for all values of n or input size n. Some algorithms execute faster for smaller values of n, but as the value of input size increases, automatically they may slow down. They may not work faster. So this behavior of some algorithm changes with increase in the input size or the number of inputs. So change in behavior of the algorithm will be able to see under the order of growth, and based on that change in behavior only we are going to have a certain categories or classes. So where we'll be seeing shortly the algorithm's efficiency, which can be analyzed by considering the highest order of n. So here highest order of n we are going to discuss shortly in the next slide. The order of growth is normally determined for larger values for the following reasons. The basic major first reason is that the behavior of the algorithm changes as the value of n increases. Of course, if we take an example of searching or sorting, if we give input size say 5 elements for 10 elements, so of course the execution time may be very limited or a very less time it will consume. But when it comes to a lakh or 2 lakh or 1,000 of numbers, when we want to search or sort, it may take more amount of time. So that change we'll be able to see, and this is what the first criteria what we need to consider, the first reason. And the second reason, in real-time applications, of course, in real-time applications, we are not going to perform searching or sorting on a limited or a 5 numbers or 10 numbers or 20 numbers. It may go beyond a lakh, 1 lakh integers or 2 lakh numbers or thousands or crores of numbers we are going to sort. So that is what a real-time situation. So for that, order of growth is very, very important. And now we'll consider one basic example for understanding the order of growth. So the order of growth with respect to 2 running times are shown here. So this is one running time of a algorithm and this is second running time of the algorithm. So in the first one, we'll be able to see clearly the running time is linear, and in the second category, it is a quadratic. So we'll be able to observe that the total time consumed by our algorithm varies here linearly, where in the second situation, its growth is what? Quadratic. That means almost doubling. So later we are going to discuss the examples as well. So now here we'll be able to see the order of growth. So in order to understand for different functions, we will be able to see a chart here. So here we'll be starting with what? A constant class. So here this is going to be a constant class where for all input size, this remains same amount of time. That means whatever the input size. So this is going to be the input size. Here it is going to be the input size for our algorithm. And these are going to be the different categories or classes of our order of growth. So starting with a constant class, coming to the logarithmic class, we'll be able to see linear class, n logarithmic n class, quadratic, cubic, and exponential and factorial. These are the different classes where we are going to add our algorithms. Based on the analysis, we are going to add under these categories. So we'll be able to judge based on these categories whether our algorithm is falling under linear category or cubic category or quadratic category or logarithmic category. So the first category called what? Constant order of growth or a class. This is where we can understand this class where we perform insertion of element into a stack, or it may be a queue, or it may be a linked list. So this is what the total amount of time required to insert any element into our basic data structures requires only constant amount of time. Similarly, deletion of element from a stack, or it may be from a queue, again it requires a constant amount of time. So that is the best example to understand the constant class. So moving towards a logarithmic class. As we all know, binary search. So how it is going to work? So especially the binary search will fall under the category of logarithmic class. And coming to the next category here, linear search will be coming under the category called linear class. And n log n, this is going to be a sorting where the most popular sorting technique what we know is quick sort. So quick sort will be falling under the category of n logarithmic n category. So for quadratic class where we perform matrix additions, matrix subtractions, so those all coming under the category called a quadratic class. And moving towards a cubic class, here we will be having a problems like a matrix multiplication, and coming to here the exponential category where we'll be having a problems like Tower of Hanoi problem, and finally the factorial problems will be coming under the factorial class. So these are what all about different classes or categories of our order of growth. So here only one thing we need to understand is that as the input size or the number of inputs increases, the order of growth increases. That means the automatically algorithms will start changing their behavior. So we would like to conclude this order of growth in this fashion, that is a constant class will be always consumes a lesser amount of time compared to a logarithmic class, and this class is going to consume always the least amount of time compared to linear, and linear class will consume least amount of time compared with always lesser than with n logarithmic class, and then followed by quadratic, then followed by cubic, then exponential, and then followed by a factorial class. So now let us move towards the next concept called understanding the basic efficiencies, that is worst case efficiency, best case efficiency, and average case efficiencies. So before we start in detail, so first, will the algorithm efficiency depends on the size of the algorithm's input alone. So this is what the question first of all we need to answer. So most of the time what we assume, the entire efficiency depends purely only on the input size. Assume if the input size is 10 for searching operation, so then the algorithm will take some amount of time. Again, if we increase the input size to 1000, again the amount of time will be consumed by the same algorithm may be different. So is it true? This is not at all true. So this question we need to understand. For some problems, the time complexity will not depend on the number of inputs alone. It also depends on some more other parameters or properties. So that we need to understand with the help of a one basic example called linear search. With this example, we'll try to understand how the algorithm efficiency, it will not depend alone on the input size. Coming to this basic problem, as we can see here, in our list of integers, we are having 1, 2, 3, 4, 5, 6. So in total, we are having an input size that is total 6 elements. So I would like to write here input size is 6. So n is 6. So when we go for applying a linear search problem or algorithm, then we may think that there are 6 elements. It may take for searching any one element may be a constant. So it is not true, because when we are looking for the same problem, if my key search element is 3, then in the very first attempt only we are going to get a match. So total number of comparisons done here are only 1. How many comparisons we have done? Only 1 comparison. In the very first attempt only we'll be getting a match. But when it comes to the key term, if I change from 3 to 6, in that case, again, first time the key element will be compared with 3, then it will not match. Again, it has to update to the next index value. Then it has to compare with 6 with 8. Again, it will not be true. Again, it has to move to next index value. Again, third comparison then, but still it is not matched. Then fourth time it is going to match. That is key element 6 will be matched with 6. So now in this situation, we'll be able to see total number of comparisons required are 4. So similarly, if I want to search the element say 100 in the given same list, so do we, by seeing the diagram, do we have 100 in this? Directly we can say that there is no 100 term in this given list of elements. But still, when we want to convey the same through the algorithm, it will start searching from the beginning index and it will end up with the last index. So though it will go for 6 consecutive comparisons, but still there will not be element presence. So that is falling under the category of what? More number of times basic operation execution. So that may end with what? The worst case scenario, that is worst case efficiency. And in the first match, whatever will be getting a key element match, that is called, or that will fall under the category of what? Best case efficiency. And between the best and worst, it may be second index value or third index value or fourth index value or fifth index value. So those are all coming under the category of what? Average case efficiency. So only now I think the answer to our question is clear. The input size is alone not enough to judge any algorithm's efficiency. It also depends on the position of the key element to be searched in a binary search or in a linear search, or it may be in any search. So depends also on the position of the elements apart from the input size. So now we'll be moving towards a new concept, that is a asymptotic notation. So this asymptotic notation is meant for representing different categories or efficiencies what we have discussed earlier. To represent the efficiency of a different classes or algorithms, we'll be using 3 different notations. Those only we call them as what? Asymptotic notations. So starting with the efficiency of the algorithm is normally expressed using all these basic asymptotic notations, and the order of growth can be expressed using basically 2 methods. The first method is asymptotic notation. Second one is using limits. So here we are going to focus more and more on asymptotic notations. So before we start or proceed with asymptotic notation, we need to understand what is asymptotic behavior. As we earlier discussed, that is, as we increase the input size for any problem, it may be searching or sorting or any other problem, automatically the change in behavior also will be able to observe for our algorithm. It may be in terms of time consumption. So that only what do we call asymptotic behavior. So now this entire we are going to follow with the help of asymptotic notations. So now big O notation. This describes the worst case scenario as we discussed in our previous slide. That is, the element in our linear search, the element or the search element may be present, may not be present, or it may be present at the last index value. So that is all with respect to a big O notation, or a worst case or maximum amount of time consumed by our algorithm. So that we call it as what? A big O notation. So this will be represented with a big O letter. So coming to the second category, that big omega notation. So what do we call big omega notation? This is what the symbol which we use, and this represents, or this big omega is meant for representing the best case. That means in the previous example we saw, in the very first attempt only we got a search successful. So that is what the best case. So that will be represented with big omega notation. Then the third one, between the worst and best, will be having a big theta notation. So this is going to be the big theta notation, which is meant for representing the average case or the average complexity of any algorithm. So these are the three different basic asymptotic notations what we use to express the time complexity or to express the efficiency in terms of order of growth. So moving towards a basic overview of our order of growth with the help of asymptotic notations, now we'll be able to see a graph with respect to x-axis and y-axis. This y-axis represents the time taken or consumed by the algorithm to complete execution from beginning to end, and this x-axis represents the input size. That is, input size basically initially it will be 0. For some algorithms or for some programs, the input size may be 0, and for some algorithms like searching, sorting and all, minimum depends on the user requirement. So this x-axis will be representing the input size, and here we'll be able to see all different categories of our order of growth, where we'll be able to see for irrespective of anything, the algorithms every time execution time is constant. This is logarithmic, linear, and log n, quadratic, and this is going to be exponential, and this is going to be what? A factorial. So now moving towards in particular the very first asymptotic notation, that is coming to a big O notation. So as we all know, big O is meant for representing the worst case complexity or worst time complexity for any algorithm. The basic definition for worst or big O notation is that it is the total amount of time consumed by our algorithm to run completely. So that is what the worst possible time consumed by our algorithm to run completely. So that we will be calling here it as what? Big O notation. So this will be represented with a basic graph that we'll like to explain here. Again, here we'll be having a total time consumed by the y-axis will be representing the total time consumed by our algorithm, and this is going to be the input size, and here this is going to be the input size 0, and here we'll be having a n naught. So this here n naught will be representing a doesn't matter. That means for some algorithms, whether it may be input size 0 or 1 or 2 or 3 or 4, up to certain limit or a certain input size, we cannot judge which algorithm is best. So for that region, what do we call a doesn't matter. So up to certain range, we cannot judge any algorithm. Sometimes it may take best, it may provide best time, or sometimes it may provide worst time. So up to certain limit, we cannot judge. So this limit, what do we call? Does not matter, and that will be represented with a n naught. That is satisfying criteria, we call it. And here we'd like to see here in our graph, this f of n is nothing but a user-defined function, and this is going to be a standard one. That is a previously defined standard maximum amount of time. Here c into g of n, this is going to be a one more function. Here this is what our actual algorithms, f of n is here our actual algorithm running time, and c into g of n is going to be the standard time consumed by any algorithm. But we are currently talking with respect to worst possible time. Here worst possible time is all about this will be represented with a maximum or standardized worst possible time will be represented with C into G of n. And that will be compared or matched with our algorithm's running time. Sometimes it may match or it may take always lesser or equivalent to the amount of time consumed by the standard worst possible time. So the same thing will be represented with the definition. In exam, we can write either this graph or we can write only this expression. In this expression, we'll be able to define the big O notation, that is the total amount of time consumed by our user-defined function or our own algorithm will always consume lesser than or is equals to amount of time compared with a standard worst possible time. For all input size, that is, it should be greater than or is equals to n naught. As we clearly see in the graph that this n naught is what? A satisfying criteria. So, up to certain limit, we cannot judge whether our algorithm is progressing or proceeding faster or delaying or consuming more amount of time or less amount of time. So that is all with respect to big O notation. So here I'd like to take one basic example. So here we are having a very first example on big O notation. That is given our user-defined function value we have got here f of n is equals to 100 n plus 5. So now the question asked here is what? Express the given user-defined function that is f of n, that is 100 n plus pi using big O notation. So for that, we all know that first of all we need to write the basic definition. So the basic definition says that f of n will be always lesser than or is equal to c into g of n for all n should be greater than or is equal to n naught. So that is what the basic definition for big O notation. So here first we would like to write what is given here. So f of n value is given. On the RHS, of course, when we look at our basic formula, so on the RHS, we'll be having C into G of n. So that C into G of n, once we write it here, so what we'll be having 100 n plus n. So this is what given. So here 100 n plus n. Here, whatever the lower class, that value we need to replace with the upper class. That means in our problem statement, they have mentioned 100 n plus 5. So this lower class, this is nothing but a constant class and this is nothing but a linear class. So among these two classes, lower class is a constant class. So that class has to be updated with its upper class. So its upper class, if we replace, then we'll be moving towards a constant class to a linear class. So for that reason, we'll be replacing 5 with a constant class with a linear class. So once we replace, then we are going to perform a addition operation. So we'll be getting with 101n. So once we get 10n, that we need to replace in our actual definition of our big O notation. So once we replace, we'll be able to see here 100n plus 5 less than or is equal to 101n. So now here, this condition we need to start checking with a hypothesis, that is n naught. So in previous graph we saw n naught as a doesn't matter section. So n naught value now we need to check with what? 0. What if we replace n naught value as 0 or n value with 0 in our program or in our definition? So 100 into 0, it will become 0 plus 5. So 5 less than or is equals to 101 into 0. That means 0. 0 less than or is equals to 0. Of course it is true. But still we cannot decide that this is only the starting or satisfying criteria. So for that reason, we need to check at least 3 to 4 values. So now n naught value I'll change to 1. The next hypothetical value I'll be taking it as what? 1. So again that 1 value I'll be replacing with this particular equation, that is 1 into 100. So 100 plus 5, 105. So again I would like to check 105 less than or is equals to 101 into 1. So it is going to be what? False. So this time hypothetically when we check for n naught value, if it is 0, it is true. But again once we check for 1, again it is false. So likewise, we need to check for 1, 2, 3, 4, at least 3 to 5 values. So based on checking, we will be getting a actual satisfying criteria starting with the n naught value as what? 5. So 5, 6, 7, 8, 9 from here onwards will be try to find every value with the definition of our big O notation. So hence here we'll be ending up with what? N naught value as 5. N naught value as 5. And what is the class? Here it is a linear class with a constant value, positive constant value is 101. So hence finally we are going to conclude that this given function belongs to, that means f of n belongs to big O of which class? That is linear class. So in this way, we need to solve a problem. Moving towards a second category, that is the second asymptotic notation, that is big omega notation. This is purely meant for representing a best case complexity or best time complexity, where this is always going to provide a best possibility. That means when we take an example of a binary search, when we are going to find a mid in our given array list, then in the very first attempt only the key term will match. So that is what will be represented with a big omega notation. Here every time the amount of time consumed by our basic operation remains the best possible. The best possible means only the number of comparisons, or it may be searching or sorting, or it may be anything, but it should fall under the category of a constant class. So that class we most of the times we add under the best case. So that will be represented with what? Big omega notation. So now the same thing now we are going to depict, or we are going to understand with the help of a graph. So once again, here we'll be having a time consumed by our algorithm. This is a 0 time, and this x-axis will be representing the input size. And in this graph, clearly we'll be able to see here, this is a standard best possible time, and whatever the algorithm we write, that may match with the best, but it may not exceed. That means it may be always what? A greater than or is equals to. There is going to be always a standardized best possible time. Whatever the algorithms we design, that may match with that one, or it may take a bit more extra time amount compared to what? The previously existing standardized time. So that is all about big omega notation. So now based on that, again we'll be having one more problem here. So this is what a definition for big omega notation, and the same problem now we need to express using a big omega notation. So here the same procedure we need to follow, but when we follow here, the class is a cubic class. So here cubic class, what we need to do in the problem statement, 10n cube plus 5. So in this we have two different classes. This is a constant class and this is a cubic class. So among these two, whichever is going to be a lower class, that value we need to simply discard. So once we discard, we will be remaining with only 10n cube. So that is what the actual solution with respect to big omega. In big O notation, we need to update lower class to higher class, but in big omega notation, we need to simply reject or discard the lower class value. So once we discard, then we'll be remaining 10n cube, and this is going to be matched with the actual definition, and that we need to check for a satisfying constant value called n0. So here, after checking for 3 to 5 random value, 0, 1, 2, 3, 4, so it will start satisfying from 0 itself. So hence we'll be writing n0 value as 0, and the order of growth, the category, it will belong to a cubic class with a constant positive value, that is 10. So hence we will be expressing finally f of n, that is a given function, belongs to big omega of a cubic class. So this is how we need to solve problems on big omega notation. So now the combination, that is the combination of that is between the best case and worst case, will be having an average case, and that average case will be represented with a notation that is big theta. And here we'll be able to see, we'll be having our user defined function and two predefined standards, one best and one worst. So for that same we'll be writing here the definition, where our function will fall between best possibility and worst possibility. So that is what we'll be able to see in the big theta notation, and based on that we'll be able to see here problem, and in the same way what we solved for best case and worst case, in that way if we solve, then we'll be coming up with a C1 with 100 and C2 with 105, and N0 will be satisfying constraint for both the categories is going to be 1, and finally we'll be representing or expressing our actual user defined function with respect to big theta of n. So this is how we need to solve the problem for big theta notation. So moving towards the final concept and very most important concept called mathematical analysis of non-recursive algorithm. So of course we all know that any algorithm can be written, or a blueprint can be written in two ways. That is, one is recursion and one more is non-recursive. So recursion is nothing but calling a body or a function itself, that is again and again. We call it as what? Recursive method of writing an algorithm. Non-recursive means what? Only one time we are going to call then iterative, we call it as what? Adding another category called non-recursive. So this is what the basic general idea, that is general plan for analyzing non-recursive algorithms. So it is a 5-step procedure where the very first step will be talking about we need to identify the size of the input for irrespective of any problem and determine the number of parameters to be considered so that we can analyze based on that. The second step is all about we need to identify the basic operation. As we already discussed, the basic operation is nothing but any instruction in our algorithm which consumes more amount of time, that we call it as what? A basic operation. That we need to identify. Then coming to the third step, we need to check whether the number of times basic operation is execution depends only on the input size. If it is depending only on the input size, then we need to compute only the worst case. Otherwise, if it is also depending on the other properties, say position of the element as we discussed in a linear search, so it may change. That means execution time also will vary. In that situation, we need to investigate best case, worst case and average case separately. So that is all with respect to step number 3. So coming to step number 4, we need to obtain total number of times basic operation is executed. That means we need to go for summation. Then finally we need to solve that, simplify that summation using standard formulas in order to obtain the order of growth for that particular algorithm. So this is the overall general plan for mathematical analysis of non-recursive. Similarly, we'll be having a mathematical analysis for recursive algorithms as well. So now, in order to understand the mathematical analysis of non-recursive algorithms, we'll take one basic example, that is finding the highest or maximum of n elements in a given array. So we are going to design, we'll be able to see here the basic algorithm design, and finally we are going to, based on the algorithm design, we would like to find the time efficiency for the same. So now this is what a pseudocode by how we are going to write, and the algorithm name is what? Maximum, and in that we will be having 2 parameters. One is array and one more is what? The size, that is n, how many number of elements we are having in that array. So here initially what we do, either if this is our array, if we take 10, 20, 30, so now we need to search, this array name is A and here size is n, that is 3. In total we'll be having 3 elements. Now our aim is to find which element is maximum. So initially, as we know, this is a linear data structure. Array is what? Linear data structure. We cannot jump directly to particular index. So what we do, we can access this array index by index starting with the 0th index, or for our understanding, I would like to change the index values to 1, 2, 3. Instead of writing from 0, 1 to up to n-1, I'll be changing it to 1 to n. So now assume what we will be assuming, whatever we will be having at the 0th index value. Now, if I change it to 0, 1, 2. So this is 0th index value, this is first index value, this is second index value. So the very first item, I will be considering it as what? The maximum element. Then based on the initial assumption, now we need to compare the second term with the maximum element. If it is true, then change the position to what? Maximum term. Again, if it is not, again compare with that one. So likewise, we are going to compare the first element with, or the first index value with all possible elements. So for that reason, in our algorithm, we'll be writing 0th index, whatever it will be having, that is 10 we are having, that we will be adding it as a position. In short, we have written it as what? POS. Now, this is our assumption. 0 is assumed to be what? A position of largest element. Once we assume 0th element, that means 10 is the largest element, but in reality that is not true. So what we do for remaining element, whenever we get more number of elements, we need to go for looping segment. So here we know the limit, the size is 3. So hence we go for finite looping statement, that is for loop. So here what we will be doing it, we'll be starting from first index value, because 0th index value already allocated to a largest element. So first to up to where n minus n we are going to check. So here first index value is what? We are having 20. So 20 now will be compared with a first initially assumed largest value. What is the largest value we assume? 10. So 20 is 20 greater than 10. Is it true? Yes, it is true. Whenever it is true, then only we need to execute this statement. So in this statement, position value, earlier we saved it as what? 10. Now we are changing it to what? I value. What is now I value? Index value is 1. So index value is 1. Now updated largest value is how much? 20. In reality, now updated to 20. Earlier it was 10. Now once again, it goes back to the looping statement. Now it will update index value I++. So now I will change to 2. So 2, that is what the last index value, 2. Now A of 2 is 30. 30 now compared with A of position. Earlier value of position was 20. So now again, once we check if 30 is greater than 20, is it true? Yes, it is true. Then again, it is going to update position value. Previously we updated with 20, now it is going to be updated with 30. So now the latest recently modified value of position is 30. So that is what the value will be retained. Again, it will go back to the for loop. Now index value will exceed the limit, that is the condition will fail, that is I should be less than or equals to n minus 1. So this time the index value exceeding to 2, that it will be updating to 3. This condition will fail. So it will exit the body of the for loop and it will return the position of the largest element. So what is the position of the largest element? That is 2 is the index value, but it will be holding the largest value, that is 30. This is how we'll be designing an algorithm for finding the max of n elements in an array. So this is all with respect to designing an algorithm. It's time to go for analyzing the same non-recursive algorithm. Whatever the algorithm we will be able to see on screen, this is purely a non-recursive algorithm. Now we'll go for analyzing the same non-recursive algorithm. As we know, there are total 5 steps to the general plan includes 5-step procedure to analyze this max of n elements. The very first step states that we need to identify the properties, parameters, input size. So as we all know, input size, what we have assumed n, and in our example we have taken input size as 3. So more than that, additionally we do not have any other parameters apart from an array. So that is all with respect to step number 1. Now coming to step number 2. So if we go back to our previous slide, in this entire algorithm, only one line has taken more amount of time. Which is that line? Can we identify here? That is a conditional statement, a line which is having a conditional statement. That is that conditional statement, what do we call comparison statement. So that line only consuming more amount of time compared to any other instruction in our program. So that line only will be holding a basic operation, and that is what the line what we are having here, a condition check statement. In that, what operation we are performing? A comparison. So hence the operation name we need to change to what? Instead of calling it as a basic operation, we need to call it as what? Comparison operation. Here our basic operation name is what? Comparison operation. This is how we need to identify the basic operation in any of the algorithm. And the hint is to identify basic operation is what? The basic operation will be always present in the innermost any of the loop in our programming language. So that is what the hint to identify basic operation. Coming towards the third step, here the total number of times, the step number 3 states that we need to count the total number of times the basic operation or comparison operation as executed, and that we need to count it. That means go for summing. So for in order to sum, of course, we'll be having a for loop that is starting from where. So for that we'll be writing f of n is equals to summation of I starting from where? The first index, because we are not starting from 0. Because 0th value is meant for holding the largest element. So 1 up to where? N minus 1. What is the ending index value? N minus 1. And for every iteration, the comparison operation has performed exactly one time. So hence we will be writing here value it as what? 1. So that is what we will be able to see here, 1. So this 1 indicates for I value 1, one time comparison is done. For I value 2, again one number of time comparison operation is done. I value, if we increase, so automatically every time it is going to execute exactly one time. So that is what's the meaning of writing here value 1. So this is what our actual sum expression. And now in order to solve this, we will be having a one standard formula, that is sum formula. That is what it says, summation of that is upper bound minus lower bound plus 1. So this is going to be lower bound, this is going to be upper bound. So now this formula we need to apply. So if we apply this formula for this, here upper bound is n minus 1. Of course, n minus 1 we are having here, minus lower bound. What is lower bound here? 1 we are having. So n minus 1 minus 1 plus 1. This is our actual standard formula to solve this problem. So once we solve this plus 1 minus 1 will get cancelled. Now we will be remaining with what? N minus 1. Again, when we remain with n minus 1, here we will be remaining with two different classes. This is constant class, this is linear class. So whichever is a lower class, that straight away we need to discard. Once we discard, we'll remain with what? N. So this is the higher class whatever will be remaining, that we need to consider. So finally we'll be reducing n minus 1 to n. So this is what we need to neglect always a lower class. So finally we are going to express this entire function, that is total time consumed by our algorithm to find max of n elements. We are going to express, that is t of n. We can write anything here. F of n we can write c of n. So I would like to write here c of n. What is the reason behind writing c of n is the basic operation name is what? Comparison. So c for comparison. Okay. So in that way we can understand for the input size n, this belongs to. Now we have meant for identifying what? Big O, that is worst possible time, because here the entire time efficiency depends only on the input size, not on the position and all. So that is what the reason, this is what the time complexity. So with this I would like to conclude. Thank you.